Dear friends, welcome to another episode of SKRAPS, a podcast where we talk to some of the most brilliant minds and explore their stories that led to moments of brilliance behind science and innovation. In case you haven't done it already, please support us by subscribing to our podcast, leaving a review if you haven't already done so. In addition, you can reach Jojo and I directly for our feedback, and our contact details are on the website, scrapsofbrilliance.com. Today, we're welcoming a good friend and a brilliant scientist. I will say this knowing a few good engineers in my life across industry and academia. Engineers always seem to have this thing about being called as engineers, and they're very specific about it and not as scientists. But our guest today has gone from working on flexible neural tissue sensors to synthetic biology to now being on the most widely quoted people in the field of enabling technologies for neuromorphic computing. If the hype is to be believed, we think that this will lead to a transformative work in this area by him and his lab members to bringing biology and technology together to spawn a whole new area of real-time artificial intelligence and machine learning. Let's hear it from the man himself, Themis Prodromakis. Welcome to the show, Themis.
Hi, Aaron. Hi, Jojo. It's really great to be with you today. Thanks for the invitation.
Yes, thanks for joining us. So Arun obviously has high praise for you in his introduction, and I'm curious, as being the non-engineer, non-scientist part of our team here, if you could sort of give us an overview of what it is that you do in your lab, especially if you're not prone to being stereotyped as an engineer. Can you describe for us what it is that you do in simplistic terms, relatively speaking?
Sure. So the way I put it to my kids is I like to build small things. So when I say small things in the nanoscale, which is essentially using a few atoms to develop devices, to develop systems, to develop, it doesn't really matter actually what we are developing in the end of the day. It's what really defines me as an engineer is that I'm using the same tool sets to build small things. So Aaron was very, very kind in his introduction to say a few things that I've done in the past, ranging from biosensors to artificial intelligence systems to tests for cell culturing and drug toxicity systems, monitors for drug toxicity. So all of these have actually utilized exactly the same tool sets that really allow us to develop at the nanoscale. For those that are listening, 1 nanometer is essentially a billionth of a meter, so about 8 to 10 atoms wide.
So, and what are some of the applications of your work? Where are they being used and how are they being implemented?
I've thought long and hard about describing what I do across a number of different people. The best way that I could sort of explain this is that my vision is to use these tools and use nanotechnologies to, first of all, learn from biology, link biological functions to engineering systems. And that would be the case with biosensing systems that we do with neural interfacing, advanced neural interfacing systems, but also study biology and learn from biology and learn lessons that we can actually go back into engineering systems and apply those lessons. And that's kind of the new emerging areas of neuromorphic computing, or revamped, if you like, because there has always been an interest in mimicking biology. But now we are developing technologies that depend on functional materials, for example, that are able to allow us to very realistically or biorealistically emulate biology. And I think that's why we see these really impressive development in artificial intelligence and hardware for artificial intelligence nowadays, which renders some amazing capabilities, obviously, for modern societies. So making, obviously our lifestyles easier and everything a lot more manageable. If it comes, like from anything from going to the supermarket, ordering stuff via Siri, or even, like for medical interventions.
So I think you're actually the perfect person for me to ask this question of. I've heard both sides of the argument, and the opinions tend to be very strong in both camps. It's about the human body sort of being the perfect machine, and that a lot of our computing principles are based upon things that are also found in biology, or the other way around. Do you have a stance on that?
Actually, no one is right. So I don't want to take to sort of sit in one camp or the other. Because if you think about von Neumann computing, like standard digital computers that we're using in everyday life so far, they are fantastic in doing some standard things that we routinely do, like a number crunching. If I was to ask you, what's the square root of a billion something, you would really struggle to tell, right? But a computer does that automatically, does it, like really, really quickly, and provides you a fantastic response. If I was to ask a computer on the other side to drive in an autonomous fashion, like a car, it's going to be really, really difficult. It's going to have a really, really difficult time to do that. And it would require huge amount of resources. Or recognizing syllabus in natural language processing that we routinely perform nowadays, with Siri, as an example, on our iPhones. And the reason for that is because the human brain does not continuously calculate the velocity that we're traveling, and how much we're putting our foot on the brakes and on the acceleration. It doesn't do that continuously in that way, and is using analog computing, and is using a highly parallel processing capability that allows us to really do that by leveraging very, very primitive components, neurons and synapses, which, by the way, are extremely unreliable. So on one side, you have something that's intrinsically highly unreliable, but highly parallel, and it gives you all this multi-parallelism in real time. On the other side, you have, if you look at the latest sort of smartphones, you have something in the order of 7 billion transistors in a microprocessor. And if you have a couple of those transistors not functioning in the nanoscale, you are in serious trouble. And they are extremely fast, yet they're not able to match the same capability. Notwithstanding, to compare also the capabilities they can deliver in terms of processing and how much power is needed. On one side, on a computer, you would actually need, kilowatts of power, for example. On the other side, you might need only 20 watts or 30 watts. That's how much the human brain consumes. So it's always a nice trick question that I'm actually using when I do science outreach to primary school kids, and I ask them, who do you think is going to actually win for this certain, a supercomputer or a human brain? And you would get massive arguments, and the two camps. So each system has actually evolved and has been developed for tackling very, very specific tasks.
I think that is one of the big reasons why we actually wanted to have you on the podcast here, Themis, because you're one of the very few people that we know of who has built tools to understand biology and also uses inspiration from biology to go back and build circuitry, etc. in engineering. And I think the field that you're working in is kind of ripe for doing that. And we will go into the details of every single system that you work on. But let's kind of talk about Themis as to how he ended up to where he is today, and what has been your journey since when you were in school. What got you into the field that you're in, or were you a bit of a late bloomer in terms of your interest for science and engineering? Tell us a bit more about that.
I'm an engineer that really enjoys his day work. So I'm really curiosity driven. I had plenty of really exciting opportunities, and I'm really thankful to people who've mentored me throughout the many years to join industry or to to change a career pathway. But I really love what I'm doing. My day life is just amazing, engaging with all these researchers and going into the office and not knowing what exactly we're going to deal with and what sort of questions we're going to start unpicking and developing. It's really fascinating. So I always tell my students that whenever you come across a challenge, you actually come across an opportunity, because a lot of people will actually give up, and the more you keep pushing towards that, towards addressing, like this challenge, it's almost certain that you would actually come across something new. The other thing that really guided me throughout the years, I mentioned, like my mentors, and I was really lucky to be affiliated and part of groups of some fantastic engineers who were not the type of conventional engineers, if I'm allowed to say so. They were highly interdisciplinary in the approach that they were taking, and that was really inspiring for me. Because I strongly do believe that innovation occurs at the cross sections of different disciplines, in very easy ways without actually you realizing. From doing simple things, I can tell you how I actually started developing cell culturing platforms, and it's an area that we've also worked together in, and that's how we met, actually, Aaron. So if I was to go a couple of years back in the past, I remember that I was working at Imperial College in the group of Chris Dumazu. That was immediately after I finished my PhD, and I had access to a really nice clean room at Imperial that I've actually helped to put together.
And interestingly, your PhD was in defect engineering. It wasn't so much in biomedical engineering or in any aspects of what you're doing.
Absolutely.
So tell us a bit more about how you transitioned from that into Chris's group at Imperial.
Yes. So as with any PhD student, I also shopped around a little bit. So I started looking at different areas that I wanted to develop, and ended up doing my PhD in defect engineering and controlling defects at the nanoscale, so that we can actually develop more efficient antennas, more efficient filters, this type of research. But in order to do that, again, I had to learn how to use these tools that would allow me to prototype devices at the nanoscale. This is kind of how I've met also with Chris Dumazu at Imperial College, who took me on board on his group in the Center of Bio-Inspired Technologies. And the reason he sort of brought me on board was because I was coming more from the prototyping, from the device engineering perspective. And Chris, for those who don't know, he's a true entrepreneur. Recently, he's been all over the news because he's providing these 90-minute COVID tests through his companies, and I kind of was tasked with the research objective to look at how we can develop more efficient and better, higher sensitivity biosensors.
And Chris has a long history of working with people, both clinicians as well as physiologists at Imperial, dating all the way back to the 70s, if I can say it, because some of his earlier papers that I've read, with his papers with Stephen Bloom, etc., are probably when you and I were both kind of kids in school, and he has kind of published some remarkable papers at those times, and he still is continuing to go strong, and he's doing really, really well.
Well, absolutely. I mean, Chris has been one of the fantastic visionaries of, and engineers, and we're really lucky to have him in the UK. He really likes to think big, right? But at that environment that I was part of at Imperial, I came across a few other people. So we had medics, we had engineers, we had chemists within Imperial, and I remember one day, Professor Sir Magdi Yacoub, who is a very well known, very well respected heart surgeon, sort of stopping me at the corridor and say, "You're doing something by making small things, right? So maybe you can help me with a problem that I have, which is I would like to grow cells in very specific locations and in very specific orientations." And my response to that was, right, so let's do that. It's quite easy. We can develop these scaffolds.
And really, for the listeners' benefit, Dr. Magdi Yaqub is one of the most premier surgeons in the world who worked extensively on, if you Google left ventricular assist devices, Dr. Magdi Yaqub was the pioneer of left ventricular assist devices using in end-stage heart failure patients prior to transplantation. So he studied the whole deal about how to implant them, what the mechanisms was of how the heart adapts to as a supportive care to prevent people from dying due to end-stage heart failure. And that is the environment. And he was a person that actually came to you and kind of said, we want systems to grow cells in that we could ultimately study heart failure and mechanisms of LVAD.
There's actually a really funny story behind this, because I've been in the UK for a very long time, and at that time I didn't really know the full extent of Magdi's, right? And Magdi, as you know, Aaron, he's a really modest person, and I remember that I was running. Because I was a little bit late for my meeting with him, to just get over coffee, discuss how we're going to grow these cells, how we're going to do this, how we're going to develop this. And I was talking to my family back in Greece, who was telling them I was rushing off to a meeting that was already late with his heart surgeon, and his name was Magdi, and they knew about him. And I felt really embarrassed, because apparently he still is a superstar back in Greece, because he many years ago he operated on one of our prime ministers, but apparently I didn't know about this. So that completely changed my perspective about Magdi after that phone call. Obviously, I really ran to the meeting immediately.
Well, and what's funny is the only reason I know anything about an LVAD, and people outside of the realm of science and engineering, if they've heard of an LVAD, chances are it came from Grey's Anatomy when Izzy cut the LVAD wires on her boyfriend. I mean, that's correct. But it's pop culture has a circle, and it comes back to science.
Exactly. Exactly. So that's kind of how, if you like, I started in that area. So I went from doing defect engineering and control of nano defects for RF and microwave devices, all the way to doing biosensors and then doing cell culturing platforms and biomimetic cell culturing platforms that then were very useful for as drug toxicity monitors. And that's kind of how we also got to know each other through your involvement with GSK at that moment. So that was, if you like, the how I went from the world of nanotechnology into the world of nanobiotechnology in a way, and during that time there was a lot of discussion about the bioelectronics medicine, obviously, in which you had a huge role in shaping this policy. And I remember this is a fantastic, a very, very exciting challenge. These guys, they're really nuts by the considering of doing what you wanted to do back then. But
I've been called many worse things than that, Themis. Thank you.
But I think it's a compliment. Take it as a compliment, because again, as I said, I really enjoy these challenges, and that's how I remember those long hours that we put in the New York summit that you organized in trying to sort of develop the landscape of bioelectronic medicines. What are the challenges? What are the opportunities? Why does it worth doing this? What do we need to do? And so many fantastic ideas came out of that summit. I think that this has been one of the most inspiring workshops that I've ever attended in my career. And that's kind of how, if you like, got involved with neural interfaces, which also the cell culturing in a way that, on one side there was the need to develop the scaffolds for growing the cells, but once you have the cells, and specifically we were looking at emulating arrhythmias on a chip, then with Cesare Terraziano from Imperial College and a few other good colleagues. But you also need to have a monitoring platform integrated into that. So that's already making, like getting into a transition into the neural interfaces, if you like, for in vitro applications. And immediately then the need then was apparent of what do you do if you want to do that at really large scale. So there's no problem, obviously, in using the same tools that I've been using for scaling the electrodes, making them smaller, increasing substantially the density. But it becomes a different problem. It becomes a problem of power consumption. It becomes a problem of data handling, essentially. So you have big data, a big data problem that needs to be processed there and then.
Yeah, and which is what led you from making or enabling technologies for cell culture and for drug screening, etc. Which, again, I'm actually proud to say that ours was the first paper that actually validated the compounds using immature stem cells and maturing them. And I think I kind of presented it to the FDA back in the day when FDA was first considering that. And that was one of the big reasons why they enabled a big workshop and a working group that is still currently running in that space to enable drug screening for cardiac toxicity. And so that's one of the reasons why you kind of moved on, and the inspiration from those cell culture enabling technologies to neural technologies came from the fact that you saw the opportunity that this was actually going to become a data problem, and this was going to be impeded by the current technologies that were available at the time, and this probably still what most people use, which is the semiconductor or CMOS-based technologies. And tell us a bit more about what that it is that you did, or how you thought of the problem and what kind of solution at a high level. And we'll drill a bit more deeper in just a second, Themis.
Absolutely. So when I hit that sort of bottleneck, then immediately my mind went, but hang on a minute. I mean, how is biology doing it? And that's where sort of it was, if you like, a nice eureka moment for me, because immediately I wanted to seek inspiration from biological processes. Look, for example, how the human retina operates. Like you have a deluge of data coming at you. The optical nerve is let alone is not capable of in communicating all of this information, like for further processing into the brain. So how is it really doing it? It's actually doing processing at the edge, processing exactly at the place where all of this data is picked up, and you only send the important information further down the line. So that was obviously was not something that I was not the only one working in this. There's something else that is fascinating in the world of engineering, is that there is a bunch of other either academics or companies all sort of racing each other on who's going to get there first. So a lot of inspiration was a lot of, if you like, of motivation through that nice competition. But the unique approach that I took back then was that I took a very important decision where I said it's impossible to do this with commercially available technologies. And even if we are able to do it nowadays, soon we won't be able to serve the needs of modern societies. Because on one side, the 7 billion transistors that I mentioned previously that we have on our iPhone, they become 7.5, they become 9 billion transistors simply by cramming more of those devices, more of those switches per unit area. And in order to achieve this, you need to make those devices smaller and smaller. And this is known as Moore's scaling law, which basically for the past 70 years, the microelectronics industry has been riding its progress on that wave. However, we've reached the point where we have devices that are only a few atoms wide, and there's not really much that we can do about this. And there are still tricks we can do there, but however, the cost rises exponentially. So then it becomes also a cost performance question. So that was the moment where I came across another fantastic mentor in my career, a really visionary, very, very different person from Chris Dumazu, a very academic-oriented person, Professor Leon Chua at UC Berkeley, who is very well known for his work in nonlinear circuits and artificial neural networks, and also is known for developing the theoretical concept of memristors, or in short, memory resistors, which are two terminal devices that have very unconventional characteristics to the typical switches that we use in our conventional electronics transistors. And I was really lucky to come across him, because I got a fellowship at that point to go and work with him at Berkeley for a year as a visiting fellow in his group. And Leon is very, very deep and thorough. He is, I dare to say publicly, he is perhaps one of the. I wouldn't be surprised if next week, when the Nobel Prizes are announced, he is among the laureates that are announced. He's really, really thorough, very, very deep thinker. But he's also a person that is giving everything to the people he's working with. So that was really fantastic period, if you like, in my career. Fantastic inspiration to be able to see and collaborate and play in that league. So what memristors are, just for the because I'm throwing at you some technical terms, and I know that our friends that are listening will be interested in knowing a little bit more about this. So they're two terminal devices, two terminal switches that change the resistance based on how much charge has actually flown through them. So if I can put it in an analogy, it's like you have a tube, and through that tube you're passing water. And the more water you pass, the larger the diameter of the tube becomes. So it's easier to pass the water. And if you reverse the polarity, the way that you're passing the water through, it actually contracts, and it makes it more difficult. So it increases the resistance. It makes it more difficult for the water to flow, i.e., the charge to flow through. Now, why is this important? This is important for a couple of reasons. First of all, it's allowing you, when you stop passing water through, let's go with the analogy of water, your device remembers the state that it was before the water stopped. So it stores it in a non-volatile way, which is really great, because imagine you have a computer and all the memory is dependent on this type of memory devices. When you switch it off and then you open your screen again, everything immediately will come back as it was. And it would consume minimum almost zero energy. So it's extremely energy efficient, but at the same time is not only able to store zeros and ones as the standard transistors that allow us to do in the digital sort of era, but it allows us to store many, many memory states per single device. So you have all of these discernible memory states that you can store. So you pass a little bit more current, a little bit more, and a little bit more, and that has a truly analog sort of character. It's a truly analog memory characteristic, which again resembles very, very nicely the memory mechanisms that are transcribed in the chemical synapses linking our neurons. So it's something that is actually coincidentally is also at almost the same scale with chemical synapses, which if you start thinking about scaling upwards these systems, and you use this as a fundamental building, I like to say Lego block for developing new electronic systems that are able to be intelligent and interact with their environment, you could take inspiration from the human brain. But in order to mimic the complexity of the human brain, you need to have very efficient primitive components to start with. And that's what Memristors were game changing in that area, because it allowed us to provide more for less. And when I say more, it's more functionality. So I've mentioned these multiple states that you can store per device. You can do that a lot quicker by conventional electronics, but also you can do that for less energy consumption and less space, which also allows you to scale it upwards.
So you came to your approach or your solution to the collapse of Moore's scaling law as it pertains mostly to neural interfaces. But this clearly has applications far beyond bioelectronic medicine. What are some of the applications that are most exciting and probably most accessible near term for this technology?
Absolutely. So the very first thing that obviously everyone is interested at is in using this as a next generation memory storage, because we live in an era that we are producing so much data that has been in fact anticipated that by 2025 we will be consuming at least a fifth of global energy consumption simply for handling the data that we produce. This data needs to be stored somewhere. Okay, so it has manifold benefits in a way. On one side, every little helps. So you can do the same type of processing, but at a much lower energy consumption. So it's a more environmental friendly and sustainable technology in the longer term. Secondly, you can actually cram more functionality into this. So the very, very first step, which is the obvious one, let's replace conventional memory technologies with this more advanced memory technology. Then the next sort of level of intervention is, because you have all this multitude of states so you can reconfigure this device to take all these different states. It means that you can also use it to reconfigure the functionality of any system. So we were familiar with FPGAs that we typically use with, and we can actually reconfigure them and develop very, very flexible sort of systems overall. But having something that is able to be reconfigured in a truly analog way, it's truly fascinating. And bear in mind that we live in a world that all the signals, that everything that surrounds us actually does require analog processing. We don't smell, see, listen with a standard, fixed bit precision. We don't do that in a digital fashion. We're continuously processing analog signals. And this is really one of the differentiating factors I've mentioned previously that modern computing architectures actually suffer from. One of the other unique points for Memristors is that it allows to collocate memory and computing. So I've mentioned the analogy of passing water through this, and as the water goes through, that's your information, you're changing in real time the diameter of the tube, the resistance of your Memristor, which means that you're also storing the outcome of your computation there. Now, this is fundamentally very, very different to the von Neumann computing architecture, which relies on having a storage medium. You go your hard disk, you go and you fetch some data, you bring it to the processing unit, you do something with it, and then you send the results back and you store it there. All this back and forth is costing us in energy, but importantly also is costing us on delays, right? So that immediately limits the type of applications, especially if you want to think of an autonomous vehicle, of a Tesla driving, on High Street, and all of a sudden, there is a pedestrian crossing the road, and you need to have a decision immediately for avoiding hitting this person, right? You cannot really afford to have electronics that will have, like a huge latencies. And to a broader extent here, because we're talking about artificial intelligence, and this is why this is so great for developing these technologies as the hardware solution, it could allow us to bring computation from the cloud to the edge. Now, but doing that, again, you have other application opportunities that that one can actually think of, because first of all, you can have real-time processing. In the case of bioelectronic medicines that your audience are interested, you can do in vivo, and in implantable devices, you can perform real processing of your biosignals. You don't need to rely on storing this somewhere or sending this via a high bandwidth link to somewhere externally, like to either a supercomputer or to the cloud for further processing. And because you don't do that, immediately your solution is more secure. Obviously, if you don't want to be hacked, the best thing you can actually do is remain off the network. So it brings other opportunities, if you like, for applications.
Yeah.
So when I buy my next car, am I going to have this technology baked in? How far out are we on this?
We're actually, although it started, I've mentioned previously about Nobel Prizes, they haven't really awarded a Nobel Prize in this area yet, as opposed to graphene. But nonetheless, application-wise, is a lot more developed than graphene. So as an example, the 3DX point solutions that Intel is producing for the servers is based on this type of devices. So the change is here. This has already happened now, and I do take a lot of pride also in my group's work for contributing in making this a possibility. Because if when I look 10 years back, the yield, we were making 1 million devices, and you would only get a handful of those devices doing something exciting, which for academia, it could be okay. You can still go and write your Nature paper and get your promotion, right? But it's not something that you could reliably exploit into critical applications like the ones that we're discussing.
Sorry to break this up, guys. Just wanted to remind you to rate us on your podcast application. So, which is a good segue to actually how you've built the infrastructure. So I think thanks so much for explaining in reasonably simple terms as to what the concept of a memristor is and the ability to do kind of on-chip computing and real-time data analysis, enabling machine learning and artificial intelligence, etc., and the fact that step change is actually happening right now with some of the chip makers. The example that you quoted there was Intel, but there's many more others. I think one of the key things that would be good to explore from your perspective is what materials go into making these memristors or memory resistors. How do they actually have? So what you described there, Themis, is more what looks like a hysteresis loop of how kind of information kind of goes up and comes back down, and then going back to the water analogy that you kind of quoted. So what is different about the materials in the memristors that make this happen, and where are the sections where your group is kind of innovated in terms of providing this? And then the next step that I want to also ask you to kind of share with us and the listeners is how you have enabled and in building some of the infrastructure that you have at University of Southampton in terms of making this to be more reliable, more accessible, and making it widely available to the research community and beyond that.
Sure, there's a lot of questions. So starting from materials, this is something that is truly fundamental as a mechanism. So it happens in everything that we have in nature, right? And I've seen some really funny demonstrations, even with people putting a couple of electrodes across their hand and measuring this hysteresis, this memory effect. In fact, I've I've written a commentary in Nature Materials a few years ago, where I was arguing that this whole area is actually as old as 2 centuries. When Sir Humphrey Davy was working with putting a couple of carbon electrodes in good proximity and using voltage pile, and he was observing discharge, and he was observing exactly the same signature characteristics, these hysteresis characteristics that you mentioned. What's different there? So why should we care now? And
Sir Humphrey Davy, who was the head of the Royal Academy of Engineering.
He was the director of the Royal Institution in the 1800s. Sir Humphrey Davy, a fantastic engineer, and he was he is an innovator. He's been known for many different things, amongst which the innovation of the electric arc. He was the very first to develop artificially made light. But I believe that he remained in history because he was also the supervisor of Faraday. So that's another interesting story that maybe we can discuss at a different time. But in any case, coming back to the materials, if you look at the periodic table, almost every single element in the periodic table can be used to enable this type of devices and this type of characteristics. Where my group and other colleagues have actually focused on, and I think this is why we were able, if you like, to develop a number of different innovations based on this, is that we focused entirely on materials that we are already utilizing in electronic technologies, in CMOS technologies. So metal oxide materials that we're using for high-K dielectrics, because we're not at the point where we could simply scrap 7 decades of innovation in semiconductor technologies and CMOS technologies, right? And which have actually had multi-trillion investments over the many years. And we cannot change the perspective of the designers from one day to the other. So all of that, there is lagging into the system. All that happens over time. So our approach has been specifically via a project that's been funded from the EPSRC in the UK. It's a program grant called Forte, which is looking at exploiting functional oxides for developing reconfigurable technologies for electronics, and we're using the same palette of materials that our colleagues that are doing CMOS technologies are using, which makes the whole thing very interoperable. Our processes compatible with the processes that CMOS engineers are using, and therefore we can take CMOS wafers as the support infrastructure and start building our emerging technologies atop of this infrastructure. So you need a little bit of the best of the both worlds in a way.
Yeah.
You mentioned about the infrastructure at Southampton. I mean, one of the nice things that we do have at Southampton is a fantastic clean room facility, which actually allows us to do all the prototyping and processing at large scale. When I say large scale, at 8-inch wafers, which is also compatible with what industry is doing at the moment. So that's quite handy, because we're getting all of the standard CMOS stuff developed via foundries in the Far East, like TSMC, for example. We get this all shipped at Southampton, and then we continue with the process, where otherwise we'll have to do that. The challenges of integration are very, very different. But you also picked up on a something else that's very, very close to my heart, and I think it kind of gave us, if you like, the heads up with other research groups, because we recognize from early on the need to be able to characterize thousands and millions of devices in parallel. And because of that, we invested heavily in my group in developing bespoke testing instruments that allows us actually to test thousands of those devices, but at a click of a button within a minute. And the moment we went through a lot of different iterations there, and once I recall that I was sitting with one of my ex-PhD students who is now working in Toshiba, and he was leading this work there. And we said, we wish we had this instrument a few years ago. We would have done so much better. And that was the moment, the eureka moment, where we said, so perhaps all the other groups would be interested in accessing these instruments and this infrastructure and this capability. And we established a startup company called the ARC Instruments, which stands for Array Control Instruments. In fact, we did it with absolutely zero investment from external sources. We just did it on our own, and that was 5 years ago. And today, ARC Instruments is exporting these solutions into over 20 countries worldwide. We have the likes of IBM, Toshiba, Huawei using our instruments into their R&D practices, and that's something as an engineer that I take huge pride, because it's one thing to do something within a very academic perspective, but it's a very, very different thing to ask, what does your users and what do your customers actually want? So that's a nice, if you like, story. That's really helped us to push the frontiers of development with these technologies further, and establish a number of different applications and demonstrate a number of different applications that no one was able to demonstrate before. In fact, earlier this year, we went all the way from artificial intelligence, coming back into smart neural interfaces. And we published a paper in Nature Scientific Reports in March earlier this year, where for the first time we demonstrated that we can actually link artificial neurons with real neurons bidirectionally in real time. And in fact, we did that also through this infrastructure that we put in place. We did it over the web, which was quite handy, particularly for this current lockdown because of the COVID pandemic. We were able to work from home and get real with artificial neurons to communicate and talk over the web. It was really, really good fun.
That might be the first example where people had actually shut down labs and only had a limited occupancy of the laboratory. So I think that's probably the first example that I've heard in the area where you've been able to still carry on work remotely, specifically catered to what you were doing in terms of your primary research aims. That's fantastic.
I actually remember that.
Which is also why the company actually also saw an increase into our sales this year, simply because people realized that with a little bit of investment, they can actually get their hands into this instrument, and they can equip their research groups to work from home, which was a really, really very, very niche, obviously, market. But it was quite nice to see that we were able to allow these people to continue with the research.
I remember when that paper came out, I was really excited about it. Even as a layperson, I could see the potential and the importance of what was happening there. And it was actually probably that posting. I think I posted it, and then Arun and I were chatting back and forth on LinkedIn at the same time. Themis, you and I were chatting on LinkedIn, and then we discovered that the three of us were going back and forth over this story and about the commonalities there. So in part, that story is responsible for bringing Arun and me together on this project. But I want to step back to ARC Instruments for just a second. Would you consider yourself an accidental engineer? Or, I'm sorry, an accidental entrepreneur? Is this what Bob Ross would kind of say, a happy accident? Or was entrepreneurship a deliberate decision all along?
I don't think anyone wakes up and says, today I'm going to innovate. Today I'm going to be an entrepreneur, right? I think this is something that naturally happens to people. I don't really like to put labels on people that, this guy is an entrepreneur, this guy is an academic. I feel that, if you just curiosity driven, you go with the flow of your research, and you get on with the research and you do the development that you need to do, at some point you actually might end up come across something that could be particularly useful for others. And I think there are great examples in amongst a number of very established and distinguished engineers that they accidentally come across something. And initially they were targeting some other innovation, something else, and they realized that what they've developed is actually good for a number of other application areas. So I don't really like to call myself entrepreneur or academic on the other side. I'm happy with the title of the engineer.
That's actually very good, Themis. I think that's also a very excellent segue into the other application of Memristors that you are kind of working on as well. So tell us a bit more about where your laboratory is going in Southampton, where the center is going with the next steps, and also where the next entrepreneurial journey is going to take you as well in terms of discovery and moving that forward.
Yeah, so I was quite delighted to receive, first of all, a additional support to engage into my next sort of stage in my career, and this came through a prestigious award from the Royal Academy of Engineering. So I received one of these fantastic awards to have, which is a 10-year support in allowing me the flexibility to realize my vision for AI hardware based on these Memristor technologies that I've developed previously. And it's a chair in emerging technologies, essentially. So where we're getting with that is in taking these mature now technologies that we've developed and the tool sets that we've developed and trying to develop specific applications that would be useful for processing data at large scale at the edge. So signal processing units at the edge, at the device level, classifiers, looking at advanced memory solutions for continuously on systems, because especially for embedded type of applications where you don't have the ability to either send data in and out and or you don't want to lose the data as well by just simply erasing the data, you need to come up with a different solution to do that. And also a new exciting area for us, which is looking at how we can actually do processing of these data, but not via statistical methods, as typically is utilized in established sort of architectures via deep learning networks, etc. But looking at doing symbolic level processing. If I was to give you an example, we are very good. If I was to ask you, what is the dollar sign of the UK? Right. If I was to ask this question into a computer, I will get like a blue screen kind of response. But immediately your mindset goes into, you must be referring to the British pound.
Yorkshire man for the answer, because they would tell you that it's not a dollar. But anyway, in very colorful language, Themis. But
yes. So being able to do processing of symbols rather than it's extremely useful, especially when you have data that seemingly come across as being uncorrelated. And that's, I think, something that brings us a step closer to both true intelligence in machines, but also a more transparent and more ethical AI, because we can use the same approaches for interrogating intelligent systems and adaptive systems when something goes wrong. For example, we've mentioned previously the example of a Tesla, right? What happens if there is if an autonomous vehicle, is involved in a car accident? Whose fault is it? Who's going to take the blame? Who's going to take the liability? There's some really interesting questions behind all of this, and of course behind the ethics of this. And because we've been looking also at implantable and in vivo and in vitro applications of these technologies, that raises even more the ethical concerns. We mentioned previously the work that we've done where we linked real with artificial neurons. What was really exciting about this work is that it was a breakthrough in the sense that it was the very, very first piece of work to demonstrate that this is possible. And therefore, if you have AI chips on one side, perhaps you can use it for replacing damaged parts of the brain in a case where someone is suffering from Alzheimer's. And if you, I dare to say, and to sort of tease you a little bit, maybe go for super intelligence. All of us could benefit from a little upgrade. Who knows?
Yeah, the guest we recently had on, Sandy Greenberg, said something that I think captures my personal perspective on the ethical application of some of these technologies, which is maybe we don't strive to lengthen life, but to improve quality of life during our natural state of living. But I think that also what you're doing, this is all sort of falling under the Sonet umbrella. Is that correct? Your company Sonet. Can you tell us a little bit more about what Sonet's doing and how it all came about?
Yes. So again, this was not an attempt from myself to behave as an entrepreneur. It was something that we were doing. We've been developing these full systems that allow us to do real-time processing of rich data sets at the edge with constrained resources, and we felt.
Just want to say this. I think you are not doing it, but we will possibly put this forward. If there are anybody who is listening, the part that got me excited, and especially also Jojo as well, when we first heard of Sonet and what the company was actually going to do, is about the limitless possibilities as to how Memristors could actually be applied and in ways that could actually have an impact on our daily life beyond just medical applications. So I think if there's anybody out there listening who probably has a few $1,000s or a few $1 million willing to, and they want to invest, this is definitely one of the options that you should be looking at. And that is my humble kind of request to all of you. So with that, Themis, you're not doing the marketing. I'm doing the marketing for you, but go ahead.
It's not humble though, because Arun, you and I are taking a piece.
Fair enough. We'll sort out a deal later on. So you're absolutely right, Aaron, and thanks for bringing this up, because really we're looking at diversifying the use of these emerging technologies for making things that we routinely do much simpler and much better. So with much less power, as I said, every little helps. If you're able, imagine running against Siri on your smartphone, right? But don't have to charge your phone every single day, because it draws so much actually power from your battery. Imagine being able to do that without, when you are abroad, let's say you're traveling into China and you need to use your iTranslate application for translating in real time from English to Chinese or whatever other language you wish to use. Wouldn't it be amazing if you were able to do that without utilizing the cloud and without actually compromising your safety and your security and your privacy, and without using your roaming? So there is many unexpected application areas there that we are targeting through Sonet. The beauty of our approach is that the chipsets that we are developing based on memristive technologies and artificial neural networks are very versatile, and they can be utilized for addressing, in the end of the day, it's all data. So having very efficient classifiers and classification systems allows us to process in real-time biosignals, spiking events, doing spike detection or spike sorting in situ, but also allows us to to recognize different syllables, and it allows to do natural language processing or image processing if needed. So the possibilities are really endless. Our motto, our vision is really utilize this technology for embed intelligence everywhere.
So, just one follow-up question to that, Themis, and I'm sure this is something that you and I have spoken of offline, but I think a question that most people who have a bit more knowledge in the area would probably ask you. I think there are quite a few number of semiconductor companies that are utilizing CMOS technologies that are also doing a lot of artificial intelligence-based chips, etc. How is the Sonet.ai chips going to be better than what's currently being explored or what is currently being developed? We can take examples of companies, but we'll stay away from that. Just to kind of, can you provide us with a differentiation argument there for Sonet.ai?
Absolutely. It's the key differentiator for us is that we're using a very different fabric for our electronics. I've mentioned previously the challenges that people are facing with, and there is some fantastic innovation from a number of different companies that are doing neuromorphic chipsets based on CMOS and very advanced CMOS technological nodes. However, this is not sustainable progress because very, very soon, when the Moore's law actually comes to an end, they will be completely surpassed by other technologies. And all of that innovation, would actually become obsolete. So our approach is that we're starting from something that already gives us an advantage. So, for example, we've demonstrated that you can do spike detection at a single channel level. We can do at least 2 to 3 orders of magnitude less power. Okay, so that is immediately something that you can put into an implantable device that will consume your coin battery at a smaller pace, or you can utilize that for scaling upwards and being able to realize perhaps Elon Musk's vision for having multi-million recording sites on these neural interfaces. So in both cases, is something that's extremely useful and it can be done simply because you're starting from a technology that is not saturated. The specs are just ahead of us to enable us to develop much more lower and more power consumption chipsets and more efficient, computationally efficient chipset solutions. So that's really the differentiating factor. And the beauty of that is that if I put my academic hat on now, through this fantastic support that we had over the years from EPSRC, from the Royal Society, and also most recently from the Royal Academy of Engineering, we have de-risked all of these highly disruptive ideas, which are, with disruption, you also have to take on board and be able to accept a higher risk. So we have already done the de-risking, and I think this is why it's a safe bet for us.
Mm-hmm. I think along with the de-risking is also the derision that you might experience from competitors or people who are set in their ways, who have made significant investments in competing technologies that are about to be obsolete. Getting them to come around and to face the music can be a tough challenge.
So I mentioned previously when you were asking me about that, what type of materials people are using for Memristors, etc. One of the unique strategies that we have utilized here is that we are technology agnostic. Although my group is developing some preferred, let's say, materials flavors, some flavors of Memristors, which we feel could potentially be the ones that TSMC will be adopting in the commercially available technologies. All of our patents, all of our innovations work unilaterally across with other Memristor technologies that other laboratories are utilizing. So that's, if you like, a unique approach that we're taking, where we are technology agnostic and our IP is on the different designs that we have established.
I'm going to bring you back over to my side a little bit. You and Arun are science and technology. I'm sort of more on the humanities spectrum. So I understand you have a love of history, and I'd like to ask you for a history lesson about Sir Humphrey Davy. And maybe you could tell us about the 200 years of Memristors and the link to Napoleon.
Oh, yes.
Which I should state is a fantastic review that Themis actually mentioned, and we will include that copy of that paper in the resources section, as well as the link to the ARC Instruments website, etc. But yeah, I mean, this will be a fantastic lesson for people who actually don't know some of this information, Themis.
Sure. So I've mentioned previously, because we talk about infrastructure and the opportunities and the challenges, Sir Humphrey Davy was really the lucky engineer, the lucky person to be around at the time where Volta has just discovered the voltaic pile. So Volta discovered the voltaic pile just before 1800s, and already in 1801, Humphrey Davy had access to loads of voltaic piles, and he started stacking them in series and in parallel to see, what's going to happen. And when he realized that if he puts them in series, he creates really large potentials, and he was able to actually demonstrate three fundamental discoveries. First of all, the electric arc, which I've mentioned previously, discharge, so the very first artificially made light. Secondly, electrolysis. And because of the electrolysis, he was the very first to be able to isolate potassium and sodium. And the next year, he actually has done a plethora of other materials. And third, which relates to bioelectronic medicines, and we didn't, I don't think if I've mentioned this to Aaron before, he was the very first to demonstrate he was one of the very first to demonstrate the galvanic effect. So by having those electrodes and those, linked into the voltaic piles, he was able to show that he could stimulate the legs of a dead frog. Now, because all of these discoveries, which I became aware of from letters that he was writing to his mother, a little bit of fun story there. Spending a lot of time at the British Library trying to go through the archives. I actually came across a few other archives which highlighted the appreciation that Napoleon, bear in mind that at that time England was at war with France. But regardless of that, Napoleon was quite excited about the scientific prospects of the discoveries of Sir Humphrey Davy. And what he did is he sent one of his secret agents with a stack of cash and a secret passport to allow him and his wife, Mrs. Davy, to travel to Paris and do a lecture on his work. And the money that he actually provided, Napoleon provided, was to allow Sir Humphrey Davy to get a servant to help them with all the traveling arrangements. So that person, that assistant, was Faraday. And that's kind of how the link was created. Of course, what's interesting is if you follow up with this, Faraday has done amazing work, obviously, later on, and a lot of his works, especially with the sulfides, can actually be classified as being very, very relevant to Memristors. So it's quite interesting to see in the history, because a lot of quite often a lot of the problems that we're trying to address in one domain has already been dealt with in a different domain. So it's always quite nice to be able to do that.
So the moral of the story then, Themis, is that no job is too small for, even if you become a big guy some other time later on in life. Faraday was still the
absolutely
student to Humphrey Davy at the time. So.
And I can argue, I always, when I give a presentation again to sort of students, I bring this example up and I ask the question, how many of you know who Sir Humphrey Davy is? And how many of you know who Faraday is? And then I tell them the story.
Yeah, this actually jives quite nicely with a theme that we've had all along, which is the value of your network. So even in the early 19th century, science was a small family, and I think we see a lot of that today. So fostering and growing your network and your personal connections, not just in the science and technology part of it, but making connections on the personal level, really has unforeseen impact on careers and lives everywhere. So I think that's a great illustration of that. So and I think I really appreciate, again, as the layperson of the bunch, that you've been able to take some really complex ideas and applications. And like I said about the artificial neuron connection earlier in our conversation, it's exciting. It's so exciting what you guys are doing, and I really appreciate you being on with us today. And I hope that we've inspired some people to take a look at ARC Instruments and at Sonet.ai and into your work at your lab. And I want to thank you for joining us.
Well, the pleasure has been mine. Thank you so much for this opportunity, Jojo. It's really great to see both of you, and I think these sessions are really exciting. I had the opportunity to listen to a few other interviews that you've done. It's I think we do need, especially in these difficult days that we're going through, some nice stories and celebrate the successes and the failures of people, because research, I can tell you, is full of failures. We shouldn't just give up, and we should just keep pressing ahead, and all of a sudden the sun will shine.
Yes, and I like what you said earlier, and I think we can all commit to living a curiosity-driven life.
Yeah, thanks, Themis. Thank you so much for coming on. Appreciate it.
Thank you.
Thank you so much.
Our sound editor is Sayantan Chandran. The soundtrack was Digger by Acid Dan. You can find their collections on Apple iTunes Store, Google Play Store, Spotify, and many other platforms. This is Arun and Jojo signing off.